So thank you, Professor Quat. So let me begin. So can you see the laser point in the middle? Okay. So hello, everyone. I'm Wenyuan Wang. You can also call me Mike. I'm a research assistant professor at the University of Hong Kong, working together with Professor Haikong Liu. It is my honor to be able to come here today to present at QCrypt and our recent work. So my talk would actually be in two parts. The first one is going to be on fully passive twin field quantum key distribution. The second part is actually going to be on passive continuous variable quantum key distribution. And the first author for the second paper, Chen Yan, couldn't come here today, so I will be actually presenting the second part on his behalf as well. As an outline, I'm going to first introduce the background. So the motivation, why do we want passive QKD to begin with? Then I'm going to introduce our previous work on fully passive BB84, which we were also very honored to present at QCrypt last year. I'm going to then introduce the first section, which is fully passive TF QKD, including the system setup, the protocol definition, the actual caveats, including the imperfect source preparation and sifting efficiency, and how do we address those, and finally the simulation results and some discussions on the advantages and challenges. I'm going to then introduce the passive DMCV QKD protocol, including the system setup, again, the protocol definition, the source characterization, Norse analysis, and finally the simulation results. So let us begin. So for the motivation, we know that active modulators, such as intensity or polarization modulators, are commonly used in QKD systems. However, they might actually introduce side channels, such as intensity correlations, and that might also be susceptible to hacking attempts, like Trojan horse attacks. So it would be highly preferable if we can somehow find a way to only use post-selection to obtain the states we want, including the decoy settings or even the polarization or phase encoding for the key, and without the use of any active modulators. That would be really nice. So this first proposal came actually in 2009 in a paper called Passive Decoy State. The key idea is that you can actually interfere two phase randomized coherent lights, here's source 1 and source 2, and that would result in correlated output at the two ports. So if you observe and post-select on one of the port, you can actually conditionally determine the state on the other port. For instance, here for the two sources, if they have the same intensity, the output would actually follow intensity distribution. You can actually observe that and post-select it into the upper and the lower portion, which have different photon number distribution, which you can use for decoy state analysis. A slight tweak to the setup would actually change this beam splitter with a polarizing beam splitter, and that instead of randomized intensities, we can now generate randomized polarization states along the Bloch sphere. Our contribution in the previous paper is actually to combine both ideas. So here we actually make use of two passive decoy modules combined with a passive encoding module. And this setup would actually give us phase randomized coherent states with arbitrary polarization and also arbitrary intensity. And Alice can actually perform local measurements on the intensity and the phase to actually post-select and prepare the decoy state BB84 states. So our paper is actually already published on PRL, and we also did an experimental demonstration, which is still under review, but it's also an archive. Note that there are also some very nice concurrent theory and experimental works from the University of Vigo and also from the University of Science and Technology of China in Hefei. So now we'll go into the first section on fully passive TF QKD. So the motivation is that we know passive BB84 now, but it would be really nice if we could combine those passive sources with measurement device independent protocols to eliminate the side channels from not only the source modulators, but also the detectors. One straightforward approach is to simply distribute that passive BB84 source each to Alice and Bob. They can just do MDI QKD. In fact, one of our team members is actually working on that project. However, a big problem here is that the sifting efficiency is not so good because you effectively have double amount of sifting. Another different approach is to use phase encoding and implement twin fields QKD, which gives us not only MDI property, but also the bonus of a better rate distance trade-off. So here in this work, we'll actually introduce a very simple but effective setup to implement fully passive CalTF QKD, which is one variant of TF QKD. And furthermore, we also introduce a set of post-processing strategy to actually address the sifting efficiency issue. So before we begin, we'll first have a brief review of what CalTF QKD is. So here, Alice and Bob chooses randomly between two bases, X and Z. In the X bases, they would actually each prepare and send coherent states alpha or negative alpha in 0 and pi phase. In the testing, a Z basis, they would actually prepare phase randomized states, but with different intensity settings, which corresponds to decoy state. For instance, they can each choose 3, so you have a 3 times 3 equals to 9 intensity settings for decoy analysis. Now here goes our TF QKD passive source. So here's actually the source for Alice. She has sources A1 and A2, so two local randomized, phase randomized lasers. Note that this is actually very similar to passive decoy state, but the only difference is that Alice actually splits off her signal classically for a phase measurement. So now she actually knows the exact phase position of phi A1 and phi A2. If she post-selects based upon the phase difference of A1 and A2, then that's exactly the same as passive decoy. However, she can also choose to post-select the absolute position for the cases where they're both 0 or they're both pi. In that case, she is actually sending alpha and negative alpha states, so you're actually doing passive encoding. So it all depends on how she performs her post-selection. The whole setup is actually looking like this. So Alice and Bob each has one of those modules. They interfere at Charlie. So here's a rigorous definition of our protocol. So first one, Alice actually passively, randomly declares an event is X or Z basis during the post-processing process. She just announces her passive basis choice to Bob. In the coding basis, she would actually observe the absolute positions of the phases, and then she would actually divide up the circumference into phase slices and choose only the cases when the slices are the same, and they're also corresponding to exactly 0 and pi, which is like the 1 and 5 slices here. In the test basis, she would actually post-select on the phase difference between A1 and A2. That's actually equivalent to post-selecting intensity, so that's just plain old passive decoy state analysis. So Alice and Bob's intensities would actually follow a distribution like this as before, and the overall domain of a 2D intensity can actually be divided up into a 3x3 grid that actually corresponds to 9 passive decoy state settings, which you can actually do decoy state analysis. There's still some caveats, though. The first big problem is that the phase slices actually have finite slice size. So it actually means the output signals actually have mixed intensities and phases. So they're not perfect alpha and negative alpha states. So this is actually a security flaw, because that's an imperfect state preparation. So how do we address this? Well, our solution is that we can equivalently think of this as signals from a perfect source, but it actually passes through a local quantum channel. This quantum channel has the property that its output is exactly physically the same as what you would get from interfering those two finite slices. However, we can actually yield those local channels to Eve and consider it as part of the external loss and error. In that way, we're actually never getting worse security, so we can actually get a security lower bound on the security and also upper bound on the phase error rate. The other caveat, of course, is the low safety efficiency. Because you have 4 independent phases, of course, the chances of actually getting 0, 0, 0, 0, and pi, 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 pi is very low. So here we propose that any combination of the slices A1, A2, B1, B2 can be used to attempt to generate the key. So some of the combinations are actually shown here. Of course, some of them are actually non-optimal. They might have bad intensity. They have misalignment. So they might actually get 0 key rate. But we only keep the cases where you have positive key rate. We just throw away the cases where the key rate is actually smaller than 0. And one more thing is that because we utilize information from all those combinations, the actual subdivision, further subdivision of the slices would only give you more information. So it never decreases the key rate. So we can slice it as much as we want, and it's only limited by the detector resolution, well, at least in the asymptotic scenario. So with that in mind, we can actually perform numerical simulation. We tried the case with infinite data case, and for the cases with infinite decoys versus with 3 decoys. We see that thanks to the efficient post-processing strategy, our passive TF-QKD only has about 1.2 orders of magnitude lower key rate than the active case, which is actually pretty impressive considering we actually have 4 independent randomized phase sources. It can also beat the plot bound even under the practical scenario with 3 decoy settings. So for some discussions, our protocol actually allows for a much better implementation security and while maintaining actually good key rate. It has some additional advantages of using no basis shifting. Alice announces the basis based upon her random bit and announces it to Bob. And we have resilience against static phase misalignment, just like phase matching QKD, because we start off preparing the states in every direction. And we are also applicable to other TF-QKD protocols like MPP and PM-QKD, which have similar signals. And it's also potentially applicable to SNS, but it might need actually more optimization. There are also some remaining challenges, though. One of them is we still lack a rigorous finite size analysis, so it will be the subject of future work. The other problem is an experimental demonstration might actually be hard, particularly in terms of addressing frequency drift, which we'll briefly talk about here. So frequency drift is a big challenge, even for active TF-QKD. However, it's particularly so for passive TF-QKD because we actually require independent phases, and we cannot allow phase lock in between the lasers. This is not a problem for the local sources like A1 and A2, because they can actually use what is called a single laser setup, which we proposed initially for passive BB84. The idea is if you have a delay line here, you can actually interfere the pulse with the neighboring pulse to simulate the effect of like 2 independent lasers. However, this trick would not work remotely for Alice and Bob, so we still have a challenging problem here. One potential solution well, in theory, that we think of would actually be the post-processing technique that's actually proposed in a recent work from the USTC group that actually tracks the frequency difference and actually compensates for that during classical post-processing. So tentative setup could actually look like this. You actually have a phase reference David, who actually sends reference lasers to Alice and Bob. Alice actually splits aside a portion of each one of her pulses for classical calibration. During the calibration, she measures the beat frequency. So that actually tells her the frequency difference from Alice to David. Bob can test the difference from Bob to David. They can announce it and compare the data to subtract it, so they now get the frequency difference between Alice and Bob. With that in mind, they can actually predict how much would have been the phase drift at Charlie, and Bob can simply rotate this amount in his reference frame to do this in post-processing completely classically. So that might actually address the problem. But we look forward to more input from our experimentalist friends out there. So now we have wrapped up a passive TF-QKD. We'll talk about passive CV-QKD. So CV-QKD has attracted a lot of attention. It's very popular in the community because it actually has high rate and low cost implementation of systems with standard telecom components. Up so far, there has been several studies of passive CV-QKD, but these are mostly focused upon thermal sources, which are relatively noisy. So in this work, we're actually focused upon the DM-CV-QKD protocol, which uses 4 modulated phases, 0, half pi, pi, and 2/3 pi, to actually encode the key. We will actually show that this protocol is in fact highly suitable for a fully passive setup. In fact, our fully passive DM-CV-QKD does not make any compromise to the sifting efficiency or the QBR. The actual setup is like this. It's actually extremely simple. Alice has a phase randomized source A. You split off part of that signal to perform a phase measurement, and you send the remainder output as the signal. And during the phase measurement, you actually have a reference laser, and you also split off the reference laser and send it outward as the local oscillator. Now, Alice actually measures the phase. It will be random between 0 and 2 pi. In the simplest case, she can simply divide it up, again, into phase slices and choose the 4 slices that correspond to 0, half pi, pi, and 2/3 pi. Now, we'll later talk about how to perform better sifting, but this is already a bare bone demonstration of passive DM-CV. Now, this is a more practical setup where you can actually have gain switch lasers to actually prepare the phase randomized pulses. And also, the signals and the phase reference would actually have a attenuator here, like a VOA, to attenuate your signal laser to the low intensity level that DMCV requires. Your LO would actually be passing through a delay and also a PBS to actually achieve time and polarization multiplexing for better robustness in the channel. Now, one assumption we have to make is a uniform randomness and also independence between the adjacent pulses. So this is actually achieved by actually using this gain switch laser that actually has a delay, like a single laser setup that we can combine the delay and simulate the effect of 2 independent lasers. We also perform an experimental verification of this uniform randomness and the independence of the phases to show that they are indeed as we assumed. Now, one last thing is that for the coherent detection, we actually measure the phase difference with this kind of a hybrid analyzer here, which is basically just 2 interferometers inside. And for photodiodes, that actually measures sine theta and cosine theta that you can actually use to deduct what the phase angle would be. So here comes the main part, the core of passive DM-CV-QKD, which we call the phase space remapping scheme. The idea is that when Alice measures her local phase, she can divide the space into 4 quadrants. In each one of the quadrants, she further divides it up into m slices. So now, whenever she looks at the slice, she can actually pair up 4 of the slices that have the same index in each one of the quadrants, which obviously it corresponds to the 4th state of DM-CV-QKD. So in that way, she can actually call this conveniently one basis. So when Alice actually measures a signal, she would actually see which basis is the signal in. And she would actually keep the quadrant information, which is actually the key encoding information, secret from Bob. But she would actually announce the basis information to Bob so that it's basically this offset angle that Bob can actually rotate when he actually sees it. So when Bob performs the heterodyne detection in the detectors, she can actually realign the phase space by compensating it classically and rotating the spaces back to the 0 point, which is like the perfect alignment. So in that way, we're effectively rotating all of those bases just to one single perfect basis that almost has no QBR or a misalignment between Alice and Bob. In that way, we can actually set the slice to be infinitesimally small, and we have no additional loss of QBR. And if the sources and detectors are ideal, we can have exactly the same Q rate as active DM-CV-QKD. So that's a free lunch. So here are some more practicality discussions. We perform an experimental characterization of the laser source, and we actually verified the assumptions on the uniform randomness and also the independence of the phases by testing the autocorrelation. We also talk about the phase resolution analysis, where we consider a common classical 8-bit analog digital converter, and we see that it actually corresponds to an angular resolution of about 0.01 radian for the passive source. So that's actually more than enough for our need, and it will introduce very little excess noise. We also analyze the overall noise that's introduced by this passive source, and we see that it's actually related to your VOA extinction ratio. If your attenuation coefficient is high enough, then we'll have actually approaching to 0 amount of excess noise that's introduced by this passive detection scheme. So we actually perform a simulation for the key rate. And as we can see, for different values of the VOA, we have different key rates. But as long as you have an attenuation ratio of more than 30 dB, your key rate is almost approaching the ideal case for active DMCV. So we see that we actually have a very simplistic but very effective passive DMCV QKD protocol that gives us much better implementation security, but has very few compromises that you have to pay. So that actually wraps up the talk. And thank you very much for listening. Here are some of the source references and also our contact info. And we look forward to your questions. Thank you very much.
I almost feel like we should have two people asking questions at once. But let's let's start with just one at a time, maybe.
Hi. So I just had two questions, related questions. So one of the motivations for passive QKD is to get rid of the imperfections introduced by active components.
Right.
So have you all analyzed the effect of imperfections in the passive components and how that would affect key rates? And
yes.
Secondly, also the imperfections in the detectors. For instance, dead times and after pulsing would introduce memory effects even, right, in passive?
Yes, that's actually a very good question. Thank you. I think for the passive components thing, yes, so in effect, we're actually changing or converting the side channels from modulators into the side channels into the detectors. But the detector is actually easier to protect, one, because it actually receives signal in the classical level. So suppose if you have a Trojan horse attack, you send in some signals, it's actually having a different extinction ratio compared to your like quantum signal in the original active case. So so yes, I think it's the idea that the detectors are easier to protect compared to the modulators. But if you actually have inaccuracies, if you have after pulses in your detectors, then you still have to factor that into the security analysis. So we're just claiming that we remove the side channels from the modulators. I think for the inaccuracies, though, I think some of our students are actually doing analysis on it. The idea is that it's equivalent to basically a knowledge. I wonder if there's some way I can draw it. Oh no, okay. So it's basically equivalent to an idea of imperfect knowledge of your modulator. So if your intensity modulator has an fluctuation, you don't know the intensity, that would actually give you a loophole in your decoy state analysis because you don't know the intensities for sure. But now for the passive case, your detection is actually imperfect. That actually gives you an accuracy jitter. So that actually would actually make your post-selection incomplete, like inaccurate. So that would also change your decoy state coefficients. So both of these actually require some kind of an upper and lower bounding. So in classical case, you can actually truncate a Gaussian distribution for the upper and the lower bound of the intensity fluctuation. In this passive case, you would actually have an upper and lower bound for the passive range that you're post-selecting upon. But that's only for the DV QKD case, though. I think for the CV QKD that we're doing here, one beauty of it is that if there's imperfect, like inaccuracy of the resolution, if you have noise in the detector, it actually goes into the X as noise. So you're actually not plagued by that problem for the DMCV. But what I've been talking about is actually for the DV QKD, including passive TF and also the passive BB84. That yes, if you have problems with your detectors, you have to model it into the security analysis.
Okay, thanks.
Okay. Other questions? Yes, there's one over there. Great. Maybe while the microphone's going over there, what's the effect of noise in the system? If you have got classical coexistence and Raman noise and things like that, or is the CV case better or worse than the DV case?
I think we haven't compared the actual key rate though, but I think it's probably just the typical comparison of just CV QKD in active case versus DV, because our rate in DV is just like a 1 order of magnitude lower than the DV, let's say BB84 or TF. Both of those are just like a 1 order of magnitude lower. But let's say for CV, probably in longer distances is not as optimized. So even losing 1 order of magnitude in the long distance, passive DV might still be better. In the close range, our passive CV actually achieves the same performance as normal CV QKD. So it's kind of like a free lunch. So I guess in the end, it's a comparison between DV and CV, I guess.
Okay, fair enough.
Yeah,
okay,
thanks for the question.
Last question over here.
Yeah, what about the side channels in your laser? Light injection attacks or whatever?
Yes, so I think we're only talking about modulators. So if your characterization of the laser is imperfect, then yes. So we're not claiming like a source independence, but we're rather claiming like we're actually independent of the modulators. So if your laser, actually not even attacks, if your laser is actually not perfectly phase randomized, you might have a problem. But we actually have a method of, I think in BB84 we have something called a pulse selection. So if you can characterize that imperfection of the phase distribution, you can actually truncate it, like throw away some additional peaks to actually make it a uniform distribution. But if you don't know that characterization, then yes, it could actually be a security loophole. If your source is actually not Poissonian, if your phase is actually not random, these could all actually be side channels. So what we are claiming is we're actually removing one of the big problems, which is actually the modulators that can have, let's say, pattern effects that can have Trojan horse attacks. Yeah. Thank you.
Okay, thank you very much. And let's thank our speaker one more time and all of our speakers for this
Thank
session.
you very much.